All right, now that we went over all of that, let's go over some practice problems I wrote. Now, keep in mind that I have access to the exam and that I have seen exam questions and that it would be reasonable if I modeled my practice problems about the exam. As we go over these practice problems, it might be a good idea to pause the screen for each one and try and solve it yourself, if you want. Starting off with central dogma, example question 1. Freddy needs to engineer a protein to act as a DNA magnet. It should attract the DNA backbone. What amino acids would be best to put on the outside, the part that interacts with DNA of the protein? So this question is asking, given the characteristics of the DNA backbone, what kind of amino acids has a high chance of interacting with it? Where interacting means like because they have favorable characteristics, they stick to each other, or they have a high chance of sticking with each other. So what do we know about our DNA backbone? We know that it has a negative charge as a result of those phosphate groups on it. And then knowing that, we need something that will interact with the negative, and that would be a positive, because positives and negatives attract. That means that we need an amino acid that has a positive charge within its side chain or its R group. So we can check our amino acid chart that will be given on the exam, and we're looking for amino acids that have a positive charge in the R group. We see that where is it? Lysine has a positive charge in the R group. Arginine also has a positive charge, and so does histidine. It's kind of small, but the positive charge is over there. So that means that we can have lysine, arginine, or histidine, because they are all positively charged and can interact with our backbone. Central dogma, example question 2. For A, B, C, and D, identify whether they are 5' or 3'. Okay, looking at this, this is a DNA molecule because we have C, T, G, and A, and thymine is only present within DNA, not RNA. And we can also see like that it is present in the double-stranded form, where it is one strand and this is the other strand. And it is asking for the directionality. So we can solve this by numbering it. Yeah, we want to number our 5-carbon base sugar, and we start with the carbon that is attached to the nitrogen base. So this is a cytosine nitrogen base, and it's attached to this carbon. It's 1', 2', 3', 4', 5'. Let's do it for this one too. 1', 2', 3', 4', 5'. Let's go to this strand. We see that this is the carbon that is attached to the nitrogen base. That'd be 1', 2', 3', 4', 5'. Carbon attached to nitrogen base. 1', 2', 3', 4', 5'. Cool. So we see that this would be the 5' end because it has that phosphate hanging off of it, and this would be that 3' end. So A would be 5', B would be 3', 3', that would be C. D would also be 5'. We see that the directionality goes from 5' to 3', and this one goes from top to bottom. It would go 3' to 5'. So we see that this matches up with our DNA molecule. I mean, our DNA characteristics that we know, which is that whenever they are complementary to each other and attached, they are anti-parallel, going in opposite directions. So A was 5', B was 3', C was also 3', and then D was 5'. Central dogma, example question 3. Given a DNA strand with the sequence, that sequence, give the 2 possible complementary nucleic acid strands given in the 5' to 3' notation. So I'm gonna be honest, this question is quite a bit trickier than what you might see on the exam, because I'm asking for the 2 possible complementary nucleic acids. Now, what do I mean by 2? Well, there are 2 kinds of nucleic acids, right? There is DNA and there's RNA. And both can be complementary or have, those base pairs with DNA. So let's see. Let's start with the DNA one first. So I'm going to rewrite it over here. TCAG A, T, A, 3'. Okay, so we know that a complementary strand must be anti-parallel, so they would go in opposite directions. And now it's as simple as looking at what's complementary. Remember our pairing rule, A and T make the word at, and then C and G look similar in visuals with that curve on the back. So what goes with T, that would be A, G, T, C, T, A, T. Okay, that is our complementary nucleic acid strand, but we want to give it in the 5' to 3' notation, so we just swap it around. Starting from this way, it would go T, A, T, C, T, G, A. Cool. All right, and then but how this is one of the possible complementary nucleic acid strands. The other one would be a strand of RNA. But we know that the pairings go from A to U, so it would be as simple as just replacing the T's with U's. So if we flip this one around, this strand would be complementary to this one. So our two strands are this one and this one, which would be our DNA one, this would be our RNA one. Central dogma, example question 4. A strand of RNA has 30% uracil, 20% adenine, 10% cytosine, and 40% guanine. What are the base proportions of the template strand that was used to produce it? So this is basically asking, you have a strand of nucleic acid with these proportions. What would be the proportions, the base proportions of a complementary nucleic acid? Because the template strand was complementary to the RNA while the synthesis was happening. So our template strand was complementary to our RNA, which means that we have the same complementary pairings. So let's just put it out. The 30% U, 20% A, 10% C, and 40% G. So because the pairings, you have the complementary pairings, you would go with A, you have an AU like Australia, like gold. So there would be this one, 30%, and then T, and then 10% guanine, and then 40% cytosine. Where this was our strand of RNA, this would be the template one. And this would be the answer. Central dogma, example question 5. Given the following template strand, determine the resulting polypeptide sequence, assuming no splicing. So we are given a template strand, which means that this will be kind of a long one. Because we have the template strand, that means we have to transcribe our mRNA. So we know that we need to get mRNA because it's asking about our protein or our polypeptide sequence. So we need to translate mRNA. So remember, synthesis of any nucleic acid always goes anti-parallel. So this would be the 3' end because it can't go in the same direction. And remember our pairings. It would be, because we are going from DNA to RNA, it would be AU. So that would be the chemical symbol for gold. It can also stand for Australia. And we also have CG, which looks similar to each other in terms of the curvature. Weird. So yeah, let's start. U goes with A, and then that would go with A. Okay, cool. So now this was our template, and using it, we got our mRNA. It is our mRNA because we assume no splicing. Cool. So now that we have our mRNA, our ribosome will come to the mRNA and it'll read it in sets of 3 nucleotides would be codons. But ribosomes always read in the 5' to 3' direction. So it would be kind of inconvenient to read backwards. So we're just going to flip it around for convenience. So let's do that right now. Cool. So now we are going in the more convenient direction. And when you're translating something, you need to look for the start codon to know when to start and a stop codon to know when to stop. So we have a start codon, which is always AUG. And then we're going to a stop codon. and there are 3 of them. So we go down, we're looking for AUG, 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 cool. And the presence of our first start, the presence of the location of our start codon determines the reading frame downward, which means like all the codons. So OG, because our ribosome does not just skip over a nucleotide, it goes consecutively, so these would be all our codons. Cool. So now we check our amino acid chart, which will be given on amino acid codon chart, which will be given on the exam. And OG would correspond with a methionine. GGU would correspond with a GGU. What is GGU? A glycine. And then GGC would correspond with a glycine as well. Huh. GGA, also a glycine. It looks like I did that to be annoying. And I hope this is not a glycine. But let's see. CGG. Okay, that would be arginine. Remember, it's possible to have 3 different codons that all code for the same amino acid because the genome is degenerate. But anyway, UGA. Oh, okay. We see that UGA is a stop codon, and stop codons do not code for an amino acid. They tell the ribosome to stop making the polypeptide, and the peptide chain will break off. That is the end of it. So our resulting polypeptide sequence is methionine, glycine, 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 and arginine, and that would be 5 amino acids long. Central dogma, example question 6. Given the following coding strand, how many amino acids long is the resulting polypeptide? So this is kind of cool. We talked about the coding strand. Earlier, we were talking about the template strand, so we had to do that additional work and find like what would be the complementary basis. We had to do the transcription. But the coding strand gives our RNA, and all we have to do is replace its thymines with uracils. So let's do that right now. And we don't have to change the direction or anything like that. Literally the exact same direction, everything is the same, but you replace the thymines with uracils. So do. Cool. And this is our mRNA. We're assuming no splicing or anything like that as well. So our ribosome always reads in the 5' to 3' direction. So we're already orientated in a convenient way. And we are looking for that start codon, which would be OG. So we want to go from our start codon until we hit a stop codon, and there are 3 of them. So we're looking for our start codon, OG, 3 of them, right? And then we define the rest of our codons according to it, because we go consecutively, we don't skip over any nucleotide. So we have these 4 codons, and we look at our amino acid chart to see what it codes for. And this will be given on the exam. So let me move this a little bit. Oh my. Okay, OG. So we know that OG codes for methionine. And what is AGU? AGU, 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 AGU. AGU, 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 AGU. AGU is serine. Easy. That is serine. And then what is UAA? Oh, that is one of our 3 stop codons. And a stop codon does not code for an amino acid. So this is our entire polypeptide. It is only, to answer the question, only 2 amino acids long. 2 is actually my favorite number, but you guys did not want to know that. Central dogma, example question 7. Below is a coding strand. Exons are red. What is the resulting amino acid sequence? This is a very similar problem to the one that we had before, in that we are given the coding strand and we want to find the resulting amino acid sequence. However, there's an additional step involved, and that is splicing, evident by the key term exons. Eukaryotic cells regulate their mRNA further in prokaryotic cells. And their primary transcript, which is the RNA that is directly and immediately produced during transcription, that primary transcript is not automatically the mRNA. it needs further steps in order to make it mRNA. So that is the 5' cap, that would be the 3' tail, and that would also be splicing. And splicing is where you take out the RNA that you do not want to be expressed, and you keep in the RNA that we do want to be expressed. So this RNA would ultimately form the mRNA that will be translated by the ribosome to produce a protein. So exons are red. So that means that this is an exon. This little guy is an exon. And then everything else by default would be introns. So that would be all the white, or all the white nucleotides. Okay, well, what are we keeping and what are we getting rid of? So I purposely made exons red to be misleading because phonetically, exon kind of sounds like that you wouldn't want it in there, but you do want it in there. And the way I remember that is that exons are expressed. And what do I mean by expressed? That means like, so because exons are actually kept within our mRNA and everything else is gotten rid of, the mRNA is read by a ribosome, and the ribosome will use the codons from the exons to produce the protein. And then the protein causes a change within the organism, so that is an expression. So exons are expressed. No, it's kind of long. And introns are not expressed. So this is the coding strand, and the coding strand gives the RNA in the same direction. Everything's the same, except you replace the diamines with uretils. So let's do that right now. Oh, but there's an additional step. We want to only include the exons and not the introns. So we skip over all the introns. Skip this over. That would be A. Nope. And then that would be U. Place the T's with U's. E, U, 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 C, A, U, U, G, A. And we ignore that. Cool. And conveniently, our mRNA. So this is our mRNA. Whereas this would just be our primary transcript. Actually, no, it would not be our primary transcript. It would be our primary transcript if the T's were used. Might be. But not really. Okay. So this is our mRNA, and it's already orientated in a convenient way because the ribosome will read it in the 5' to 3' direction. Let's look for our start codon. OG. There it is. And then the start codon determines the codons, the reading frame following suit. So we have 4 codons over here. We know that OG codes for methionine, UUU, that goes with phenylalanine. I do not know what CAU does, so I can check the amino acid codon chart. That will be included on the exam. That would be CAU. Where is that? Histidine. And then finally, UGA. We see that UGA is a stop codon, which does not code for an amino acid. So this is our entire peptide chain produced. We see that it's pretty short. It's only 3 amino acids long, and it would have been longer if we kept the introns in, but because we did that splicing, remove the introns, our resulting mRNA is smaller.
I thought you were going to say
just say it. No. Just say it. It's one word. Josh, it's not funny. Just say the word. Josh.
I'm trying.
It's one word, Josh. It's right there. Just say it.
Give me a second.
Josh. Josh, just say the word. Holy cow. Josh, I'm wasting their time. Just say it. Match. Oh my god. Okay, so I asked Joshua to come in here because I did not have the energy required to say match with an exclamation mark, but I did not think it would take that long. Okay, thanks, Josh. Oh Christ. Okay, whatever. Okay, so we're matching. We're matching left and right. So replication. So replication involves you have your DNA and then you synthesize a new copy of DNA for it. So we are synthesizing more nucleic acid, which means this involves a polymerase. And because we're synthesizing more DNA, this is a DNA polymerase. Now, translation. Translation is where you read the mRNA, and it is read by something to produce amino acids, which will make the protein. Josh. So translation, what reads that mRNA are ribosomes. And mRNA processing is only present in eukaryotic cells, not prokaryotic cells. So these are like some of the different mRNA processings, whatever. So we have the 5' cap, we have the 3' tail, and we also have splicing. Now, what is transcription? That is RNA polymerase because it is the only option left. But also because, so transcription involves reading a strand of DNA and making an RNA transcript of it. And that would involve synthesizing more RNA, which is a nucleic acid. And because we're synthesizing more nucleic acid, you need a polymerase. And because it's RNA, it is an RNA polymerase. I like having a brother. But anyways, central dogma example question 9. Classify the following mutations. Okay, so we're looking at this one. We have UUU, we have UUA, and this looks to be our mRNA. And only one nucleotide was changed, meaning that this is a substitution mutation, which is also kind of point mutation, in that only one nucleotide is changed. But UUU, that would be phenylalanine, so PHE, and UUA would be UUA, leucine. So because we are the substitution resulted in a new amino acid being coded for, this is a missense mutation. Okay, GGU to GGC. We see it is also a substitution point mutation because we only changed one nucleotide. So that would be I don't know. Okay, it would be glycine for GGU, and it seems to also be glycine for GGC. So we went from a codon that codes for glycine to a different codon, but one that also codes for glycine. So because we ended up with the same amino acid, the codon was different, but same amino acid, this was a silent mutation. Now, silent mutations are harmless. Yeah, they didn't affect our actual structure. CUU, that would be leucine. CCU would be proline. Oh, also a substitution mutation. We only changed one nucleotide, which would be the middle one. And because we went to a codon with a new amino acid, this would be a missense mutation. Cool. So let's look at the rest. AAU. Okay, that would be adenine, ASN, and then UAG is a stop codon, which does not encode an amino acid. So because we went from a functional, something that coded for an amino acid, to a stop codon, this is a nonsense mutation. Now, nonsense mutations tend to be a lot worse because they can greatly truncate your polypeptide because you introduce a stop codon early on, so it makes your peptide much shorter than the regular one, or it can. If you had the nonsense mutation very close to your original stop codon, you might not change that many amino acids. Okay, so over here it's kind of long, but we'll get our mRNA, and it looks like we're giving an OG, so this is our start codon. So our reading frame goes down this way. And let's look at this one. So still our start codon, we still have that. This is our new frame, right? So we see that these are our 4 codons, and you're looking at over here, it seems like we're missing 2 U's. So what happened was we had a mutation that resulted in 2 U's not being represented. So this was a deletion of 2 nucleotides. In addition to being a deletion, it seems to have also been a frame shift mutation because the reading frame was changed. Over here, our reading frame resulted in the following amino acids after our start codon, which would be UUU, AAA, and GGG. Over here, now we have UAA instead of UUU, and we have AGG instead of AAA. And that changed all the codons, which would change most of the amino acids downstream as well. So this was a frame shift mutation. But it was also a deletion of 2. Hey, thanks for helping me, bro.
Ugh.